Hello, everyone, and welcome to today's webinar in the CERTUP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERTUP and ESTCP. This webinar will consist of a brief overview of the two programs, followed by a technical portion which will feature applications of compound-specific isotope analyses, or CSIA, to ascertain contaminant degradation and identify contaminant sources. Dr. Paul Hatzinger of Aptim will give an overview of CIA basics, provide theoretical and real-world examples of how CSIA data can be used to document degradation of a variety of contaminants, and then he will discuss the current state of the art in forensic evaluation of contaminants with a focus on perchlorate and distinguishing sources of chlorinated solvents during vapor intrusion studies. We will pause midway through Paul's presentation for a Q&A session, and we will conclude the webinar with a longer Q&A session. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use with Zoom. If you lose the content on your screen or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please feel free to call into the conference line shown here. You may also submit a comment using the chat box, but only use the chat box for comments related to technical difficulties because the Q&A option should be reserved for questions for the speaker. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A periods to submit your questions. We do encourage you to submit questions as you think of them. And when you do submit your questions, please make sure to add your organization name at the end of your question so that we can identify you during the Q&A sessions. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of CERTUP and ESTCP, and also the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with CERTUP and ESTCP since 2001, and before that, she served as a research leader at the Battelle Memorial Institute, where she conducted scientific research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University in Maryland. Andrea?
Thanks, Rula, and thanks everyone for joining us today on our webinar. Before we jump into Paul's presentation, I'd just like to tell you a little bit about ourselves and what we're doing here today and the big picture of technology transfer. CERTUP and ESTCP are the DoD's environmental technology programs, and how they differ is that CERTUP is our science and technology program. Really, this is our research and development. And it is operated as a partnership between the DoD, the Department of Energy, and the Environmental Protection Agency. And we've worked very closely, really co-manage CERTUP with ESTCP, which is our demonstration and validation program. And typically what we see is the knowledge or the technologies that come out of CERTUP as they mature, they move into ESTCP to demonstrate these concepts or technologies in the field. And very importantly, overall, is then to transfer this knowledge or specific technologies out to end users so that it's used in the field. Slide 10. So we have a couple of big drivers that push our program in terms of what we look at. And number one is sustaining our ranges, facilities, and operations. And this is a very broad perspective. This can be from sustainable forward operating bases to dealing with issues of noise around our military installations, toxic air emissions and dust, maritime sustainability, UXO. A lot of different issues encompass sustaining our testing and training ranges. Slide 11. And then we also deal with reducing our current and future liability, and that can be dealing with contamination from past practices, and the webinar we'll hear today is helping us to address that particular issue. And this also includes the pollution prevention to control life cycle costs. And so we do a lot of work here on elimination of different hazardous materials or processes on our installations. Slide 12. So what all of this work culminates into, as I see it, is that we need to transfer the technology to the field, and that is a critical aspect of our program. Slide 13. We do this through a number of different ways. We've got different training videos. We've done in-person training, guidance documents, manuals, and we also have an EnviroWiki. All of these materials are found on our website listed here. And then, of course, we have our webinar series, which is really here to put out the latest information, the latest knowledge, tools that we've been developing. Slide 14. So I encourage you to look at our webinars coming up. They are all listed on our website. Registration is open for most of these, and you can see it really spans the spectrum of the various different technologies and issues that we're addressing under the program. Slide 15. You can go to this link for any of the upcoming webinars. You can register for them in advance, and all of the information as well from these webinars is archived on our site. So you can also go here and look at past webinars to see what was provided in the past. So Rula, at this point, I'll turn it back to you for our webinar.
Great. Thank you so much, Andrea. It is now my pleasure to introduce our speaker, Dr. Paul Hatzinger, who is the Director of the Biotechnology Development and Applications Group at Aptum. Paul has more than 25 years of experience in contaminant biodegradation, bioremediation, and forensics. His research group has been instrumental in the development and field application of new remedial approaches for several contaminants of concern to the DoD, including perchlorate, 1,2-dibromomethane, NDMA, MTBE, and nitramine explosives. Paul has also conducted extensive research on the application of CSIA to determine the sources and fate of perchlorate in the environment, and he maintains a strong interest in furthering the use of stable isotope technologies for environmental applications. And you'll hear about that today from him. Paul has authored more than 80 peer-reviewed papers and book chapters and has served as the PI on research grants from NSF, EPA, DOE, CERDUP, ESCCP, and other organizations. He holds a bachelor's degree from St. Lawrence University and a master's and doctoral degree from Cornell University. And Paul, I'll turn it over to you.
Great, thank you, Rula. So today we're going to take a little tour of stable isotope analysis and how we can apply this to many of the different contaminants of concern that we have at sites within DoD and other areas. So just as a quick overview, I'm going to start and talk a little bit about fundamentals and then move into applications, particularly for chlorinated solvents, looking both at documenting degradation, daughter product degradation, as well as a little bit about source discrimination with vapor intrusion. We'll have a pause for some Q&A, and then I'll move into some emerging contaminants or other contaminants of concern, including 1,4-dioxane, dibromoethane, and perchlorate. And then a quick summary, and we'll wrap it up. So as a practitioner, you know, what can you use CSIA for? So what are some of the questions that this technique can help you answer? Is my contaminant degrading? Are its daughter products degrading? That's a big question that comes up with CVOCs. What's the dominant mechanism? Particularly dual isotope analysis can help you determine mechanisms of degradation. What are rates? What are approximate field rates? And finally, is this my contaminant anyway? So there's a forensic aspect of this. So just a few slides on fundamentals so we're all on the same page. What's an isotope? Well, if we go back to our basic chemistry, isotopes of an element have the same number of protons and electrons, but a different number of neutrons. So if we look at the figure, carbon-12 has 6 protons, which is what defines it as carbon, and a light carbon isotope has also 6 neutrons. But there's a version of this, C13, which is also a stable isotope. It's not decaying, which has an extra proton. So this one is has the same 6 protons. I'm sorry, it has an extra neutron. So it has the same 6 protons that make it carbon, but an extra neutron. So its charge mass ratio is a little bit different than carbon-12. What we're not talking about here are radioactive isotopes, things like carbon-14 that are decaying with time. So again, on some fundamentals, here are some commonly measured light isotopes. And if you think about the suite of contaminants that we have in the field, you know, chlorinated solvents, we have hydrogen, carbon, chlorine. So you can see that there are elements here where you can do isotopic measurements. Oxygen is common in ethers like 1,4-dioxane or perchlorate or nitrate. And then nitrogen and sulfur species, you know, we see in pesticides, we see them in explosives, particularly nitrogen. So you can see there's a lot of potential applications here. And on the right, this just kind of shows the concept that in nature, generally the light isotope is dominant. So this is the percentage of the light isotope on the right in each case. But there are a few instances like with chlorine where you have a fair abundance of the heavier isotope, chlorine-37. Okay, so why are these things useful? Well, compounds can have very different isotopic ratios depending on how they were formed. You can see a scenario where, for instance, you have a naturally formed compound. Perchlorate or nitrate are good examples of that. And also synthetic versions of that. So where there's been a contamination issue, and maybe you want to know whether this is a natural contaminant or a synthetic contaminant in the field. Secondly, you can document degradation very frequently by looking at isotopic shifts. So there are predictable shifts in isotopes as bacteria degrade specific contaminants or as they degrade abiotically. So this is a means where you can go in the field and document that something's degrading, it's not being diluted, it's not volatilizing away. So you can see where there's 2 important aspects of stable isotope analysis. Okay, so how are these ratios measured? Well, there's specialized instruments that do this. They're called isotope ratio mass spectrometers or IRMSs. Now, these are designed specifically to look at ratios. They're not very good at looking at chemical concentrations. Now, when chemicals are analyzed individually, then we call this CSIA or compound-specific isotope analysis. So you could take a sample from the field of a fuel spill. You could run this through an IRMS, and you could get a bulk isotope value. However, if you run it through a GC first, so you split those individual compounds, you know, perhaps benzene and toluene, for instance, and then combust those to CO2, you're going to get individual isotopic measurements for each of those compounds. So separately, and that's what makes it compound specific. And this is always a bit confusing. So how are these ratios reported? So basically, they're reported relative to known standards and is what's called a delta value. So essentially, someone will say, well, you know, the DC13 is this in per mil, so you have this odd symbol, which is basically a part per thousand. But essentially, in these cases, this delta C13 is the ratio of carbon-13 to 12 in a sample, minus that in a standard, and there are international standards for each of these different elements that are used, you know, broadly among labs, divided by the standard, and that becomes a very small number. It's usually, you know, a couple of points beyond the decimal point, so this is multiplied by 1,000, generally to give you whole numbers. So if someone says the delta C13 is plus 30 per mil, all that means is there's 30 parts per thousand, or about a 3% higher ratio of C13 to C12 in the sample relative to a known standard. And you should note that this value can be positive or negative. So a compound can be isotopically enriched or isotopically depleted. Okay, so now what is fractionation? And this is really critical and important, particularly when you're looking at degradation of contaminants. So there's slight differences in bond strengths between heavy and light isotopes. So if you have a carbon-12, carbon-12 bond versus a carbon-12, carbon-13 bond, say in TCE, there's slight differences in bond strength, with the bond that includes the heavier isotope being a little bit stronger. And this results often in what's known as the kinetic isotope effect. And this impacts many abiotic and biological reactions. So for instance, if we look at this example, we have TCE. In this case, this is a dihalococoides, let's say. It's being degraded to cis-DCE. We're all aware of that reaction. But what happens over time is that we see a decline in the concentration of TCE, so we have less of it, but we're also seeing an isotopic enrichment. So we see a higher ratio of the C13 TCE compared to C12 TCE in the product. And conversely, with the daughter product, in this case cis-DCE, we start out with a low concentration. Assuming this isn't degrading, it gets higher and it's depleted isotopically. So this is getting isotopically lighter, the parent is getting isotopically heavier, and essentially this is isotopic fractionation. Now, just a little more detail, and what I really want to do is kind of explain this concept of what's called the enrichment factor. So what I just said is that you have different rates. So as TCE degrades, you're going to have a slightly slower rate for degradation of the C13 TCE compared to the C12. If we compare the ratios of these, that's known as a fractionation factor, or alpha. And then there's a version of this known as an enrichment factor. And this is really what you'll be thinking about typically when you're looking at samples in the field, is this enrichment factor. And what it is essentially is a means to look at how much enrichment you get as something is degraded. So if we move over to what's known as the Rayleigh equation, this is an equation that basically looks at the fraction of a chemical that's remaining versus that amount of enrichment, or that epsilon value. So if we look at this graph below, this is a figure from a paper looking at the degradation of 1,2-dichloroethane, or 1,2-DCA. And what we see here is on the x-axis, we have F, or fraction remaining. So we have 100%, 80%, 60%. So the compound is degrading. On the y-axis, we have the delta C13 value of the DCA. And what we see here is for one reaction, this dehalogenation pathway, we get a very quick and steep enrichment in the delta value of C13. So if we take the slope of this, and if you plot this as a natural log, and I'll say that people who do isotope work plot these in many different ways, which sometimes leads to a bit of confusion, but this would be linearized if we plot this as a natural log, but the slope of this line is that enrichment factor, or epsilon value. They're typically negative, and in this case, this shows a very strong fractionation, or very strong enrichment in the carbon isotope. Conversely, with the oxidation pathway, the chemical's still degrading with time, but what we see is that we only have a slight enrichment, or an epsilon value of about -3 per mil versus -32 per mil for the hydrolytic pathway. Okay, so enrichment factors. You're not going to determine these yourself typically unless you're a scientist that does this. So they're best determined in a lab setting, either with pure cultures if it's biological, or pure mineral if this is an abiotic study. Enzymes, you can do this enzymatically. They often vary among degradative mechanisms, but they should be reasonably consistent for the same mechanism. And if you're looking to employ CSIA in the field, then you really want to have an enrichment factor of at least, on the order of -2 to 3 per mil. Because, if you're taking samples from a well, if this is a groundwater issue, there's always mixing issues in the field, and enrichment tends to be muted somewhat in a field setting. And I'll always say more isotopes are usually better. So if you can get dual isotope or triple isotope analysis for a chemical, you can gain a lot more information than using one isotope, and I'll provide some illustrations of that. Okay, so where can you find these epsilon values? I'll give you two sources here. There's an EPA document from 2008 that has a table which gives you relevant epsilon values for lots of different types of reactions with solvents and some other chemicals, MTBE and a bunch of others. And then there's a database online called Isofrac. And essentially it's an Excel spreadsheet, and it's a compilation of fractionation factors from lots of different, or enrichment factors from lots of different papers over time. And if we look, this is just an example from the Isofrac database. If we take a look at this, and essentially what we have here is our compound of interest, cis-DCE. Here's our epsilon value. Here are the conditions, or the presumed mechanism of the reaction, and then you have the reference on the right. And just to show you some differences, so this is if you have zero valent iron catalyzed degradation of cis-DCE. Here's an example of relevant epsilon values for that. They're relatively high. This is something you could very clearly see in the field. Conversely, when we look at an aerobic degradation mechanism by co-metabolism, in this case toluene degrading bacteria, it's extremely low. So if for some reason you suspected this is a mechanism in the field, you probably are not going to get a lot of information from isotopic enrichment, because the reaction doesn't enrich significantly in this case. If we drop down to the bottom, here are some examples from studies where reductive dehalogenation is going on. Most people are aware of that and interested in that. It just shows you there's a range, and that range, but again, a fairly high epsilon value from about -15 to -27 per mil. So here are some sources, and there's lots of contaminants in these different databases that you can take a look at. So how do we sample for these? What are some strategies? Can we look at daughter product degradation? I'm going to kind of run through that now and then just finish up before the first Q&A period with a case study, and then a little bit on vapor intrusion. There's some really nice work supported by CERTUP ESTCP that's looking at ways to forensically look at vapor intrusion using CSIA. So how do you sample for stable isotopes? The good thing is it's something that most of us who do field work are used to doing. You can use low flow sampling. The minimum concentration of CVOCs typically is on the order of 5 ppb, although the methods are getting better so that you can get data sometimes with just a few ppb of a contaminant of concern, or a CVOC of concern. Typically, the labs that do this commercially will send you 6 VOA vials to do the sampling. It gives them extra sample, and often they run the same analysis multiple times. At the same time, you should do your normal geochemical analyses and collect samples for VOC analysis, because as I mentioned, the lab will typically ask you for the concentration, or it has to be run by typical 8260. There aren't specific hold times for this, and just an idea of general cost, are on the order of $500 to $600 for the initial compound. So if you have a site where you have TCE, cis, and vinyl, let's say, you can usually get stable isotope values for all 3 of those from a single sample, assuming concentrations are high enough. And the second or third sample are often quite a bit less expensive. Okay, so which wells do I sample? What's a strategy? So part of that has to do with the objective of your work. Is this an M&A evaluation? Is this an active remedial technology? But some of your options include sampling along a groundwater flow path. And I'll show you some real data from a site in a second, where you're looking for enrichment as a function of transport and groundwater flow. Another option is sampling an individual well over time, particularly if you have an active technology where you're looking at declining concentrations sort of in a small area or in a batch system. You can employ both strategies. And as with any other technology of this type, where you're looking in the field, a good model is critical. Understanding groundwater flow rates and paths and what likely mechanisms might be. You need to use this always along with your typical, concentration data, geochemical data, your typical means to understand the processes that are occurring in the subsurface. Now, another thing that's important, if you do enough of this, there's times when you get a snapshot in time, and you're trying to interpret data from several wells that were just, taken as a snapshot and get some understanding about what's going on. But one thing that's extremely useful is knowing what the original isotopic ratios were for some of these solvents. Now, these are some data from the EPA guidance on this. And essentially, it's just looking at things like PCE and TCE and what were the range of C13 values in these materials to begin with. And there is a range, but you can see, for instance, with TCE, we're somewhere around -23 to -34 per mil. And with both TCE and PCE, we kind of have a mean right around -30 per mil. But this is important to know because it can kind of give you some guidance when you don't have a lot of data about whether, in fact, you're seeing degradative losses. And here's an example. This is just kind of an instructive example of a site. We have, some wells where we have very high concentrations, maybe NAPL concentrations. We're moving down gradient with groundwater flow, and we're looking at isotope values. Well, the first thing that's pretty clear, we have these very high concentration zones here, 100,000 ppb, and we see that we have a isotope ratio for TCE, and this is the DC13 of -35 per mil in this well, -25 per mil in this well. Those are both within the range of parents. So the first thing you might think about here is, wow, could these be different sources? It's possible that this is just TCE that's degrading, but it's also possible that you had different spills here. So there's a forensic aspect of this. Now, as we move down gradient, what we see is we're seeing enrichment in carbon-13. So we're at -20, -19. So we're getting enriched as we move along, and along these fringes again, this material is getting consistently heavier. As a snapshot, this is a great indication that you've got degradation occurring as you move down gradient in this plume. Now, the next slide is sort of the counter to that, which is a site where, whoops, let me just back up here. Preview. Okay. So the next slide is a counter to that, where we have a site where, again, we have these same sort of starting concentrations, but as we move down gradient, we're not seeing a lot of enrichment. But if we said, okay, well, this is -25 and this is -30, that seems to be enriching. But what might really be happening here, again, based upon groundwater flow and what, say, we know about mixing at that site, is what's happening is these two sources are mixing together. And what you would expect if we have a 50% mixture of MW1 and MW2 groundwater as we move down gradient, you would expect an isotope value that's in between. So this is additive. And you'll get, -30 per mil. And as we move further down gradient, there's always going to be some variability, as there is in concentrations and anything else at these types of sites. But what we see is we don't see a lot of evidence of degradation occurring here because these isotope ratios are very similar. Even though as we move to the fringes, we're seeing, lower concentrations. And I'll say that, I've looked at some of this data over time where it was suspected that there was degradation going on. And in fact, because concentrations were declining, but some of this isotope work was done. And in fact, what it showed is that, some of the down gradient wells weren't really capturing the plume very well. So concentrations were declining. But what happened is, when the well was put in, you kind of missed the core of the plume. So what was really happening is, you're not getting any degradation at that site. Now, there's always interest among those that do work with solvents on daughter products. This is your typical reductive dechlorination pathway. And, there's sites where we know there's cis-DCE stall, or you get accumulation of vinyl chloride. And often the question is, well, are these daughter products degrading? So essentially, if we look at this figure, and let's assume this is TCE and cis-DCE. So for daughter products, so isotopic enrichment alone is not necessarily evidence of degradation. And what can happen, and perhaps we're moving down gradient, the parent is degrading. So in this case, we see the parent TCE is biodegrading, it's being enriched, and it's producing this daughter, which is cis-DCE. But as the parent gets heavier, the daughter product also gets relatively heavier. So if you're just looking at the cis here, you might say, wow, you know, it's definitely biodegrading. I see enrichment. But in fact, all that's happening is the parent is going to the daughter and the daughter not degrading further. Now, one way that you can look at this again is sort of this starting epsilon value or starting delta value rather for the TCE. So if we assume this to be negative 30 per mil, the parent's getting heavier, the daughter product cis is getting heavier, but when we get to the point where the TCE is largely gone, that value for the daughter product will never get heavier than the original parent if it's not biodegrading. So this will never go beyond negative 30 per mil. So that's kind of one way that you can sort of look at this. Now, if that daughter is degrading, so if we say cis is degrading to vinyl, then often what will happen, the parent's degrading, the cis is biodegrading, and you'll go well beyond that negative 30 per mil. And, you know, in a more complex figure, you might have vinyl chloride and then ethene in here as well. So you can see, you know, you can then see values of cis that are going to be heavier than that negative 30 per mil. Okay, so here's some data from an actual site. And this was a site where bioremediation was performed, and there was bioaugmentation, addition of lactate, and then later on, emulsified oil was added. And this was a large plume of TCE and cis-DCE, and the technology worked pretty well. But then 5 years later, as part of a ESTCP project, we went back and tried to understand whether degradation was still occurring, and there was a little bit of TCE left, and there was quite a bit of cis left. So we sampled 4 wells along a flow path. These are all screened in generally the same interval, and these are just the contours here for cis-DCE, and it gets as high as about a ppm, and this is 100 ppb, and sort of moving down gradient. So the question was, using stable isotope analysis, can we see whether cis-DCE is degrading and whether any TCE that's remaining is also biodegrading. So here's what our TCE data looked like. Again, low concentration, so we're able to get data from 4 to 8 ppb. So we started our negative 30 per mil, we presumed, and the first thing we notice is that everything is isotopically heavier than our presumed starting TCE concentration or any TCE source materials that at least have been analyzed at this point. And we're seeing enrichment as we move along the flow path down to a point where we have no detection. It's a nice sign that we're getting isotopic enrichment and we're seeing continued degradation at the site. If we look at cis and go back to what I mentioned previously, the cis at this site is very heavy. So negative 8 per mil, that's much, much heavier or much isotopically enriched compared to the starting TCE. That's certainly evidence that the cis is degrading. And again, as we move down gradient, and these are real site data, so this is what you'll see. So we see that we're heavy, this well, everything is a little bit lighter, but still quite a bit heavier isotopically enriched compared to the starting TCE. Then as we get to the end, and this was only a 2 ppb sample, it's extremely enriched down at the end of this plume. So very good evidence also that the cis is biodegradable. Now, a lot of people are always interested in rates. Can you determine anything with CSIA in terms of rates of degradation in the field? And there are different ways to do this. This is just one example of a means to simply try and look at rates. And the interesting thing with doing this is that this can be done independent of concentration. So we're always looking at concentration data. You can also look at isotopic enrichment with a series of assumptions and use that as a measure of degradation rate, or at least the constrained degradation rates or half-lives in the field. So essentially, if we use that same TCE isotope data that I showed you previously, and here's on the x-axis, we have distance from the original source well, the 114A, moving down gradient. We get a plot here. And basically that as we get this plot, we have a slope. And that slope is basically a measure of the increase in the delta C13 value in TCE as a function of distance moving down gradient. We can do the same thing for cis. And again, these are real world data, so there's some scatter. You know, perhaps at a site like this, if you're truly interested, you do a snapshot first, and then you go out and if you see indications of this, you know, sample some more wells to try and fill this out a little bit better. But again, we have a slope here of the DCE isotopic enrichment as a function of distance down gradient. Now, if we make some, back up here. If we make some assumptions, say from site models of the velocity, you know, groundwater flow, 2 feet per day, and our epsilon value, and of course we can plug different epsilon values into this, then we can actually determine a K value or a rate. And essentially, this term is kind of what we're seeing in terms of these slopes. And by making assumptions about groundwater flow rate and our enrichment factor, we can actually determine K values or rates and convert that to half-lives. So this is a way independent of concentration to try and get a measure of rates of degradation in the field of contaminants. And there are more complex, certainly ways to do this, but I just wanted to give you an example of how this can be done. And this was done through ESTCP project ER 201427. And I'll mention that on a lot of these slides, the relevant ESTCP projects are cited, so you can go back. There's reports for most of these projects online and papers, and all that's available through the CertUp ESTCP website. So now, before we go into the first Q&A, I want to talk a little bit about vapor intrusion and using CSIA to try and understand sources of chlorinated solvents in indoor air. So basically, the concept here is if you have what you think is vapor intrusion in a house or an office building, there's always the potential that, in fact, the solvent that's in the vapor in the air there is actually from an indoor source and not from a contaminant source in groundwater. So that kind of lends the question, well, you know, in consumer products, are there still CVOCs? And the answer to that is an overwhelming yes. Gun cleaner is 90% TCE, pepper spray, PCE. There's lots of different potential sources of CVOCs in consumer products. And certainly these could, get in the air in your house. So the concept of this, and this was an interesting project by Thomas McHugh at GSI, as well as Tomas Kuder and Paul Phillip, University of Oklahoma. But the basic concept here is that, and this is where I'll sort of introduce also a dual isotope concept, is that we know for manufactured sources, and I kind of showed you some of those data, what the parent range of carbon isotopes and chlorine isotopes will be. So we have that sort of constrained in this box. Now, if we get into the field and say we have a TCE plume also running under this building, and if in that TCE plume we're getting degradation, then we'd expect that source TCE to start to fractionate or to become heavier in both carbon and chlorine isotopes. So we have this effect where it's possible that in the groundwater, our isotopic value for this compound is actually well out of the range for manufactured sources. So what are the possibilities then? So here's our indoor source. This is a sample from our indoor air. And this is a sample from the subsurface. So essentially, if we take a sample and in the indoor air, we're right within that range. And in our subsurface source taken from the groundwater, we're well out of that range, not only out of that range, but in a trajectory that we'd expect from fractionation, then what we see is that this is pretty good evidence that in fact that vapor intrusion is not vapor intrusion at all, but it's from an indoor source. And the converse of that is if your subsurface source and your indoor air source are both out of the sort of parent range and very close together along a fractionation trajectory, that's tough to say, then this is a good indication of vapor intrusion. And then here we have potentially a mixing situation where you possibly have two different sources. Just finish with one example. This is a vapor intrusion example. This was from Raritan Arsenal, New Jersey. And essentially what we have here is we have a TCE plume. We had some indoor air TCE. Summa canisters were used to sample the indoor air. Isotopic analysis was done on TCE in the groundwater. And if we go down to our simple legend, what we see is that the indoor air samples group very nicely within sort of the parent range for DC13 and delta CL37. And the groundwater samples were out of that range. So the TCE was fractionated. So this is a nice real world example of, basically showing that in fact, this was not a vapor intrusion source from the groundwater. This was an indoor air source of TCE at this site. And I'd encourage you to go look at the final report for ER 201 025, and there's a lot more data and a lot more examples in that report. So now it's time for our first Q&A session.
Great. Thank you, Paul, for a great introduction to the topic. We've received a number of questions. Can you tell us if there are any modeling or analysis tools that have been developed to help evaluate isotopic data?
Modeling tools to evaluate isotopic data. Well, certainly geochemists, and I'll mention, there's a lot of very good geochemists who do this type of work, and they can be based upon, enrichment factors and that type of thing. They can do a very good job of modeling expected isotopic ratios in daughter products, as well as parents as biodegradation occurs. There was an effort, and Paul Phillip, I believe, was involved in that through ESTCP to try and really start combining CSIA into a much more complex, site model, just like you would do with concentration data. I don't know offhand the status of that project, but there was an effort going forth to try and really combine this with, your normal type of site evaluation models, almost like when you would use concentration using isotopic enrichment. I can sort of check on that and sort of get back on that.
Great, thank you so much. Another question, does volatilization cause fractionation?
Well, with to a slight extent, but with these types of compounds, with chlorinated solvents, it's certainly sorption and volatilization, say from groundwater to some extent, are not going to cause the types of fractionation typically that you're going to see with destructive mechanisms.
Great, thank you. Can you elaborate on why you need CVOC concentrations to perform a CSIA analysis?
Well, in part of it, it's just for the analysts themselves, so they know, what concentrations to put into their instrument, whether they need to dilute so they don't overwhelm the instrument. If you have a NAPL and, if you have 100 ppm in one sample and 5 ppb in the next, they're going to have to dilute those samples in order to get them in range, just like you would with a, typical 8260 mass spec analysis.
Great, thank you. Can you tell us whether you can use CSIA to distinguish CVOC sources in groundwater as well as for vapor intrusion, and whether you're going to cover this more in the second portion of your presentation? Yeah,
good question. I'm not going to cover that further. And I'll say this, there were differences, obviously, when I just looking at TCE, as I showed you that figure from the EPA, you have parent source materials that vary by 12 or 15 per mil. I think the difficulty is overall at DOD sites and others, these solvents were often used over many years and they were often used in the same areas. So, you can get mixing, and it's very difficult to kind of weed that out. Now, a place where this can be useful is if you have at the same site, you have, say, sources that are where groundwater flow from, one location is not going to go through the other. So you have separate sources that are not going to commingle, and you see large isotopic differences between those. As kind of I showed in the example, that's a case where potentially you might not be able to determine what the original source was, so who made the TCE, but certainly on a site-specific case, that provides very sound evidence that, okay, and particularly let's say it's a NAPL situation or it's an aerobic aquifer where you know degradation isn't going on or you see no evidence of daughter products, then you can say, okay, I know I have these two sources, I know they're not degrading and fractionating, and there's a large difference in the isotopic signatures of these. So that's an indication that, in fact, you have two different sources. And of course, there's always questions with litigation for that type of thing. But I can also defer to looking back at the 2008 EPA guidance, because they do provide a couple of pages talking about forensics, as well as a study which shows a PCE site where, in fact, they were able to separate sources based upon understanding the geology and the flow paths, but also using isotopes to show that they were very isotopically distinct.
Great, thank you. This is a question from the government of Alberta. Typically, when we are trying to determine if environmental contamination is causing indoor vapor intrusion issues, we use subslab vapor sampling instead of indoor air sampling. Does the isotopic approach provide an advantage over a subslab vapor sampling approach?
Yeah, that's a really good question. And I'm going to be honest with you, I'm going to defer to some of the experts in that area. And I would say, Thomas McHugh at GSI would be a person potentially to get in touch with about that. I think isotopically, you could probably look at, typically when this has been applied, to my knowledge, you're looking at groundwater and you're looking at just the indoor air. In terms of, doing subslab isotope analysis, I'm sure that could be done as well. And I don't know, if you have a subslab source that's coming from groundwater, I don't know that you can also presume that that's the same source within the building, because you still could have, I presume, if you don't have pathways to enter the building, you could still have an indoor source or a mixed source with the subslab. You probably can't easily discern unless you use something like isotope analysis. But that's kind of all I can probably give you on that. And I would defer to, vapor intrusion folks who've done some work with CSIA to follow up further.
Sounds good. Thank you, Paul. This is a question from the U.S. Army Corps of Engineers. Can groundwater samples collected using passive diffusion samplers be used for CSIA?
I don't see why not. I don't see why not. I would, the first time that's done, it's probably worth doing a comparison with the lab. So doing a passive sample, and then, just your typical, say, low flow sampling in the same well, just to compare the results. But I don't see any reason that you couldn't run those analyses with groundwater samples collected through passive samplers.
Thank you. A question from ExxonMobil. Are water samples solvent extracted prior to quantification by isotope ratio mass spectrometers?
They're not for, there are instances where that can be done. One example is for explosives. So it's not uncommon to, collect samples for explosives and then do, on solid phase media, extract those off of the media. And then, you can do isotope analysis, and Neil Sturcio at University of Delaware is doing that type of work. For chlorinated solvents, typically, this is just done in the water phase. For some of the other contaminants that I'll talk about, and I know, the method with 1,4-dioxane, I'll talk about that in a few minutes, but that's a method to concentrate using sort of a carbon matrix and then thermally remove that from carbon. So there's some different techniques whereby you can run this type of analysis. And there are a few instances where there can be a solvent extraction portion of that.
Great, thank you, Paul. One more question, and then we're gonna get back to your presentation, and we'll answer the remaining questions in the final Q&A. This question relates to what amount of fractionation should be observed before concluding something other than environmental noise?
Yeah, really good question also. And that really gets to the heart of you know, the precision of analysis. Now for VOCs, you're typically on the order, and this is just sort of instrument variability of about, you know, 0.5 per mil, somewhere in that range for carbon. Chlorine is probably in the same area. And for those that are doing hydrogen or deuterium, that's quite a bit larger, you know, up to perhaps several per mil. So that's just kind of your instrument variability. And then as you get into the field, you know, the thing that often occurs is these effects are somewhat muted in the field. And a lot of that has to do with mixing. If you're taking, you know, if you're taking groundwater from a well, you may be pulling from areas where you've got a good deal of degradation going on, perhaps where you don't have very much, or you're mixing with clean groundwater. And that can, you know, that can mute some of these effects that you see in the laboratory with pure cultures or with enzymes or with pure minerals. So I can't give you an exact value like it has to be 2 or 3 per mil. You know, part of that's going to depend on your system, the number of samples that you have, and the extent of isotopic fractionation that the reaction causes. You know, the nice thing with that Rayleigh plot is at different levels, you can be at least somewhat predictive and say, okay, you know, I'm only going to see a 1 per mil shift at 80% degradation of this compound. That's almost not going to be detectable in the field because of the instrument variability, as well as the fact that I know that this is going to be muted. But if you have an epsilon value of 30 per mil, it doesn't take a lot of degradation of a compound to start sort of getting well above that, you know, 0.5 or 1 or 2 or 3 per mil difference in terms of degraded and undegraded compound.
Thank you so much, Paul. Please proceed with the second part of your presentation.
All right, thank you, Rula. All right, so I'm going to finish up today, and I'm going to talk about some other contaminants of concern that hopefully you guys are interested in. 1,4-dioxane, that remains a large issue. I'm going to talk about EDB, which for some reason never becomes a large issue for the most part, except at a few sites. And then a bit about isotopes and perchlorate. So 1,4-D, I'm sure many of you out there, you know, have heard of 1,4-dioxane. It was a stabilizer in TCA, but I should say it's also found at a lot of TCE sites around the country where there was no evidence of TCA use. It's very miscible. It's not particularly volatile. It doesn't partition to carbon, so it's one of these things you don't sorb. It forms very large plumes that are occurring at chlorinated solvent sites, and it's becoming, you know, of increasing concern. The nice thing is it's pretty readily biodegradable under aerobic conditions. Now, not under anaerobic conditions. So if you have an anaerobic treatment technology for TCE or PCE, you're very unlikely to degrade any 1,4-dioxane. It's going to remain at the site. But there are bacteria that can grow on this and degrade it aerobically. So they're using it as a carbon source and oxygen as an electron acceptor. And then there's also a lot of co-metabolic degradation. And for those unfamiliar with that, so a co-metabolic reaction is basically one in which there are organisms that have these enzymes. They're often monooxygenases. They grow on a substrate, and for 1,4-D, these are things like propane and ethane and tetrahydrofuran, which is another ether that can occur at 1,4-D sites. And they grow on these, so they form biomass and CO2, but this enzyme or sometimes multiple enzymes that they generate are what we'll call promiscuous, so they can degrade other things. And there are a number of these that can degrade 1,4-dioxane, and they take it through to an intermediate. And the only difference in some respect between these organisms and that can grow on the compound is whether or not they can further metabolize this intermediate, which also tends not to be particularly persistent. Anyway, so there was an interesting paper a few years ago by Dave Adamson and a series of authors, Hunter Anderson of the Air Force, Shaili Mahendra, Chuck Newell. And what they did is they went out and they looked at sites, and they tried to estimate, based upon site data, groundwater models, half-lives of 1,4-dioxane in the environment. And what they found, interestingly, was that at some sites, had half-lives on the order of a year or two. So this is half-lives in months. This is just % of wells in a study. But essentially, there's cases where this seems to be attenuating or degrading. Now, this could just be dilution. It could be, other factors. And there's other sites where maybe, these half-lives are much, much longer, on the order of many, many months. But the other thing they found was they found a positive correlation with sort of half-life, so lower half-lives when there was higher dissolved oxygen, and they found a negative correlation with concentrations of VOCs and metals. Now, we know there's aerobic degradation processes that occur, which help explain this, and we know that both VOCs, and particularly 1,1-DCE, as well as some metals, can be toxic to these types of reactions. So then that brings the question, well, geez, is degradation occurring at these sites? Is biodegradation occurring? That's the source of natural attenuation. Can we stimulate that somehow? And can we document it? Other than just sort of looking at concentration data, is there some way we can document this process? So there's a project. This is a CERTUP project, ER 2535. It's run by Haley and Aldrich, and Peter Bennett is the PI. And basically, they've been making great inroads into CSIA for 1,4-dioxane. And they're using a dual isotope approach. So this case, looking at both carbon and hydrogen isotopes. And while there's very limited data to date, very limited fractionation data, what you see is that for carbon fractionation, and this is a paper, the reference is in the back, and also there is a report on the CERTUP ESTCP website for this project. But we see organisms that co-metabolize this, and all three co-metabolize. They're fractionating carbon from somewhere on the order of about -2.7 to -5 per mil. So not a tremendous amount of fractionation, but you're in that range where that should be something you can start to see in the field. And there's a lot of hydrogen fractionation. Now, as I mentioned previously, hydrogen isotope analysis, there's a lot more variability. You just have to live with that. But there's also a great deal more fractionation that occurs. And if we look at this one strain, this strain K1, it grows on tetrahydrofuran. And this was the strain that fractionated the most. Now, the one thing we know is that this enzyme that allows this organism to grow on THF is the same enzyme that allows the organisms that biodegrade 1,4-D through growth also to live on 1,4-dioxane. So the expectation could be, and I only know of one data point, and it was a carbon data point for the main organism 1190 that people have studied in terms of its isotopic enrichment. But this certainly suggests that there is a potential in the field through this technique to document the biodegradation of 1,4-D at field sites. And it is a commercially available technique at this point. So this is something that, again, there's more work that needs to be done, but a lot of work in developing the method, and the beginning work and looking at fractionation has been done through this CERTUP project. And I think there's going to be a lot of field application of this moving forward. So from there, I'll move to dibromoethane, or EDB, and it's not really emerging, it's just forgotten. It was a fumigant used in the 80s. It was a lead scavenger in leaded fuels. It's still in aviation gas, and it has the second lowest MCL of any of the regulated compounds for drinking water at 50 parts per trillion. So this is in the range of what we're concerned about for PFAS, certainly. And this is a pretty well-known carcinogen. So is it out there in the environment? Well, it probably isn't, right? Nope, it is. It occurs widely in groundwater above the MCL. And this was and the problem is by typical 8260, where you're looking at fuel hydrocarbons or other things at a site, you're not going to achieve this 50 ppt MCL, so you have to use another method to do that. But in some nice work done by Ron Falta a number of years ago now, they sampled throughout South Carolina, and they looked at percent, and these were old underground storage tank sites, percents that were exceeding the MCL for EDB versus the concentration. And here's the MCL at 50 parts per trillion, and all of these samples exceed the MCL. And you could see in South Carolina, it was about 50% of the samples at that time. EPA went on to do some state survey work. And again, it was on the same order, about 40%. So, there's a lot of EDB out in the environment above its MCL. Good news is it's readily biodegradable, both anaerobically and aerobically. It also degrades through hydrolysis, which you kind of can't stop from occurring. So it is slowly degrading with time, and it reacts with sulfide minerals. So I just wanted to show you, I mentioned that, fractionation or epsilon values need to be determined in the lab. And these are some data from ESTCP ER 201331. And this is just going through that process. And this was work done by Paul Koster van Groes at Aptum and Tomas Kuder down at University of Oklahoma. And essentially what we see, again, fractionation, isotopic enrichment for dehalogenating organisms, and these are cultures that not only degrade chlorinated solvents, they also degrade EDB, dihalococoides, and many of these other organisms. Dehalogenemonas degrade EDB. We see that we get, interestingly, for many of these organisms, they're mixed cultures, get about a -8 per mil enrichment factor. This one culture in a study was much higher, probably indicates that there may be a different mechanism occurring. Which is quite interesting, or a different dehalogenase that's causing this. Aerobically, and this is a methanotroph, so an organism that grows on methane. This is a co-metabolic reaction. This is an organism that was isolated up in Cape Cod that degrades EDB. It also grows on ethane and propane. And we see much less fractionation, but still measurable fractionation. Just for comparison, iron minerals, pyrite, iron sulfide, you get a strong fractionation, although it differs among the different minerals. And then just by straight hydrolysis, you see you're getting a fractionation of about -20 per mil. Now, this can be a fairly slow process, but when you have a compound that's been in the ground potentially for the order of 5 or 6 decades, this can become very relevant. I'm just going to give you a case study. This is former Kirtland Air Force Base. The Air Force had a large fuel leak there for a number of decades, leaked avgas, which contained EDB, as well as some other fuels that didn't. It's a very deep site, which makes this problematic. And if we look at the figure, this is sort of a source area or a NAPL area on the base. And then this is the outline of the 50 part per trillion contour of the EDB plume. And this is probably 4 or 5 years old now. But essentially, you can see it sort of flows up the base under neighborhoods. It's very, very deep in the ground, but still, of course, it's a concern. But there was a lot of question early on about whether this was attenuating and what those rates might be, or whether this is just a plume that's going to go on and on and on. So through ESTCP, through this same project, 201331, methods were developed, and the issue here is you had very low concentrations. We're dealing with 50 parts per trillion. So this is a case where you had to develop methods to deal with those low concentrations and concentrate the EDB. And also you had some locations where you've got NAPL and high hydrocarbons, so you have to look at EDB within those hydrocarbon areas. And Tomas Kuder at University of Oklahoma did a great job in sort of advancing these methods. That's published in an ESTCP paper as well as for this project. But this was one of probably the more interesting sort of isotopic field studies that I've seen, in that what you see very clearly, we don't know exactly what the source delta C13 value was for EDB, but we assume it's somewhere around negative. There is some evidence of, around negative 29 or 30 per mil. But if we look at this site from the NAPL area moving down gradient, we see a huge isotopic enrichment in EDB as we flow along this path from, negative 10 or 12 per mil in the persistent source area, which is also enriched compared to what we assume the source could be. Now, so maybe this is aged out to the point where, you're even getting, degradation in this region where, this source is being degraded. I'll talk about that in a second. But also as we move down gradient and potentially into, a much more aerobic zone, we're seeing, really significant enrichment in carbon isotopes here. Now, as we sort of move over, if we look at these sort of well designations, then this is moving along the flow path, we're kind of here in the source area. There's still a lot of benzene and other hydrocarbons up in this area on base property. And you can kind of see, more higher concentrations of EDB there. And then we kind of reach a point where the benzene is attenuated, and then we just have EDB sort of in this down gradient zone. Now, if we look at this isotopically, what's really interesting is up in the source zone, there's some sort of bouncing around, but we don't see a lot of fractionation here. And in part, and this is a good lesson, if you have a NAPL, if you have TCE, in this case, the NAPL would probably be EDB dissolved in hydrocarbons. But as your compound of concern diffuses out of that NAPL, even if it's being biodegraded, it's being replaced at some rate by fresh compound that's coming out of the NAPL. And that can really mute any isotopic degradation that you would see. So it's possible in this zone that either there's not much degradation going on, we don't know, we don't think that's the case, but more likely that as degradation is occurring, it's, the EDB is being replaced by unfractionated or less fractionated EDB from within the NAPL. Now, as we get beyond that NAPL zone, we see this huge enrichment. And this is probably a case where you're getting anaerobic degradation of the EDB biologically, or maybe through some sulfide minerals. And you're seeing this large fractionation over a fairly short zone. And then we get into this longer part of the plume, we still see fractionation. And this, based upon the studies that were done for this project, this is very consistent with what you'd expect due to hydrolysis over a period of many years or decades. So again, a slow process, but one that fractionates and one that you can see using stable isotopes. And I'm going to finish with just one more study, and this is purely a forensic study, and this is perchlorate. So this became an issue 20 some odd years ago now. It was detected in a number of sites, and the paradigm at that point was, well, we're not going to see a lot of this around the country. It's used at rocket testing sites, manufacturing areas. There's probably a fairly small handful of locations where you're going to find significant perchlorate. So that seemed like good news. And then better methods were developed. You find, contaminant concentrations of contaminants always become a problem with better detection methods. And then EPA started requiring testing. And essentially what you started seeing perchlorate popping up in all these areas around the country where there was no military site, large areas of West Texas in water. So what happened? So the question is, well, are there other sources? Are there other non-military sources? And there are. And some of those are synthetic, the rockets, fireworks, flares, those types of things. And basically, Sandy Desgupta with some others went through and tried to sort of estimate environmental impacts of these materials. But there's also a naturally occurring perchlorate in the Atacama Desert of Chile. And this is basically the driest place on Earth. It has been for many, many, many centuries. And you get salt accumulation in the surface, and that salt accumulation is very high in nitrate. And this is a photo of Andrew Jackson and some researchers who are collecting this high nitrate caliche material from the Atacama. At one time, this was a major source of nitrate for both fertilizers and for explosives. And there was a large war that occurred, the War of the Americas between Peru, Bolivia, and Chile, basically to gain access to this resource. and the first major sea battle of World War I in 1914 between the Germans and the English were fought because the Germans blockaded this resource and the English needed it to make explosives. So England won that battle, and shipping occurred again for nitrate to England to make explosives. But that's kind of an aside. But more importantly, this material was widely used for fertilizers, including throughout the United States, and it contained early on about at least 2% of a naturally occurring perchlorate. And that could be a large source term, particularly in agricultural areas. Now, the third source of this is what we'll call indigenous natural perchlorate, and perchlorate forms in the atmosphere all the time. But when you get dry environments like the Southwest, Western United States, Death Valley, areas of California, it accumulates in the vadose zone, kind of like the Atacama, but at a much, lower rate. However, as we go to large-scale agriculture, we start growing cotton in the high plains of West Texas. There's a lot of irrigation, and that material then gets moved to groundwater, and all of a sudden you've got groundwater contamination with perchlorate. And is it possible that it's this natural material? So if you went back 15 years, I don't think anyone would have said, oh, either of these were very large sources in terms of groundwater contamination. I think everyone was thinking, well, this is all synthetic material. CERTUP ESTCP funded a number of different projects, and there were a lot of groups involved in this work: USGS, J.K. Bulkey, Neil Sturcio, Andrew Jackson at Texas Tech, Greg Harvey with the Air Force, Bawa Gu at Oak Ridge, a whole suite of people who did, myself at Aptum as well, but a whole suite of people who did sampling, developed methods, and tried to really understand, first of all, can you distinguish these sources of perchlorate? And secondly, what's their occurrence, not only in the United States, but globally? Now, isotopically, very good methods were developed, and perchlorate, of course, is Cl O4-, so we have isotopes of both oxygen and chlorine, and there are multiple oxygen-stable isotopes, as well as chlorine-stable isotopes, and a radioactive isotope of chlorine that actually becomes somewhat important in this, but that's kind of outside of the scope at this point. So really good methods were developed. A question came up before about sampling. In this case, small ion exchange resin columns were typically used. They're attached to wells, and then perchlorate contaminated water is pumped through the resin to collect the perchlorate, which is then extracted and purified off of the resin in order to do the isotopic analysis. Whoa. Okay, so let's just back up. So basically, looking at sources, the one thing that became very interesting is, if you look again, now this is dual isotope analysis, chlorine versus oxygen isotopes, you kind of had these three groupings. You had a grouping of synthetic perchlorate, you had another grouping of Chilean material, and the blue points are from the Atacama caliche materials, the green are actual fertilizer samples. And then you had this group out of Southern High Plains in Death Valley, where you were basically kind of had this range, and it was kind of interesting because each of these were sort of separated isotopically if you do this sort of dual technique. Certainly by concentration or other analyses, there's no way to tell these perchlorates apart. They all look the same. And there's also more of a story here with the oxygen isotopes, but just for time and simplicity, I'm just going to stick to looking at the chlorine versus oxygen. Now, final case study here. This is Rialto, California. There were basically two large synthetic plumes in Rialto, and there were two different sources of these plumes, and you can kind of see them flowing down gradient here. And essentially, everyone kind of knew in these high concentration areas this was synthetic perchlorate, but this question arose about wells that were contaminated, down in this area to the southeast, and then across a couple of faults down in the Chino subbasin. These are concentration data down to the southwest. And there was an interesting newspaper article which showed this plume. Now, the direction of groundwater flow is in this direction. So here is the Rialto plume. But you can see based on concentration data, this plume deviates into this huge lobe that runs down into the Chino subbasin. Now, water would have to cross these faults, and there were questions about whether that's even possible. But just looking at concentration data, it appears what we have here is concerns based upon these two plumes with synthetic perchlorate in these different areas. And some of these are drinking water wells, so it becomes a significant issue. So isotopic analysis was done, and this was project 200942. USGS, John Isbicki and Nick Teague did a lot of sample collection at a lot of large wells for this. And essentially, isotopically, all of the material in the synthetic plumes, isotopically grouped with our synthetic perchlorate, those are the red diamonds. So that matched up perfectly. But as we got down to the southeast, as we got down into the Chino subbasin, all of these samples grouped with Chilean type perchlorate that was presumably applied as fertilizer decades ago when these were orange groves and agricultural areas, and that's moved into the water and persists under aerobic conditions. And isotopically, those are these blue diamonds. So you can see it grouping in with these Atacama type samples, and the fertilizer samples in this case are the blue circles. These are all of the actual groundwater samples. And then you got a few areas where you've got mixing of presumably some synthetic material as well as some of this Atacama material. So this technique proved invaluable to try and look at sources of perchlorate throughout this region. And within all of this, there was a bit of indigenous natural material mixed in, and there were other techniques used, and particularly radioactive chlorine to show that. And you can look at some papers or the report from this project to get a little further understanding of that if you're interested. So I'm just going to wrap up. In terms of CSIA, this is a great way to provide direct evidence of biodegradation or abiotic degradation of many contaminants. It can be useful for generating rates apart from concentration and discerning mechanisms, particularly with dual or triple isotope analysis in cases. You can sometimes discern degradative mechanisms and potentially even in situ. There are cases where this can provide good evidence of contaminant source identification, and it is commercially available for a number of compounds, including CVOCs and 1,4-dioxane. Some of the limitations, you need relevant, fractionation or enrichment factors, and some understanding of the degrading reactions to interpret the data. The data are rarely ideal. When you go to these talks, everything's a straight line. And I showed you one example where that's not the case. And typically when you get field data, those field data are not perfect, but often they're interpretable at different levels. And often they can be used to develop a much greater understanding of what's going on at a site. And the final point, these results should always be evaluated with geochemical, hydrogeological, microbiological data. You don't want to use isotope data to propose anaerobic degradation of VOCs in an aerobic aquifer, right? It makes no sense. So all of this should be used in light of what you already understand about your field site or your situation, but it can be excellent supporting information. I'll end there. For further information, please visit the CERTUP ESTCP website. Clearly there's been a huge effort put into developing CSIA techniques. There's a lot of different really good researchers who've done this. A lot of it's funded through CERTUP ESTCP, and these techniques are available commercially. There's a lot of university lab people as well as government people who are more than willing to talk to you and help you out in terms of interpreting data. How do you sample? How can these techniques help you?
Thank you so much, Paul. This was an outstanding presentation. We have a whole slew of new questions for you, starting with this one. In your experience, at approximately what percentage of sites does CSIA provide degradation or rate information? And how would a user know if CSIA might be worthwhile?
Yeah, that's a tough question. I don't know that I can give a percentage, and in part because I think it's an underutilized technique. So I think you have to start with what is your question. If you have a site model and you have occurrence of a lot of daughter products, and you're showing degradation is occurring, then it's really supporting information. If you have instances, however, where I see this being even more useful is, natural attenuation situations where maybe these occurrences are at relatively slow rates, but over long periods of time. There's potential there where you can use CSIA to sort of get you out of the weeds. And if you see the strong isotopic enrichment, you can say, okay, yeah, this is definitely a degradative process. This can't be sorption or volatilization or, that type of procedure. So I would say that it's not applied widely enough to really say, okay, what percentage of sites are using this. Another example again is cis DCE stall for chlorinated ethene sites. Is cis DCE biodegrading? I showed you that can be tricky, but again, with the correct interpretation, you can gain data and potentially supportable data to show that, yeah, in fact, degradation is occurring, and maybe this is a natural attenuation situation rather than having to do an active remedy and the costs associated with that.
Thank you. And maybe related to this a little bit, I think you've convinced us all that CSIA is a powerful technology. Why is it not used more frequently?
Yeah, part of that I think is a technology. Well, there's maybe two aspects. One is a technology transfer aspect. So it's sort of getting project managers and site managers and consultants to understand that these techniques are there. They're well defined at this point. The sampling is not very hard. So part of that is just getting everyone who has sites and manages sites to understand that. A second part of it might be regulatory acceptance. So people like John Wilson have been beating this drum for a long time, scientists within EPA. But it's really getting through to the regulatory community as well, because the problem with some of it is that there's not established EPA methods. So it's not like 8260 where you have to follow this exact procedure. So you've got to educate all communities in sort of how this works, and also work with the analysts to make sure that appropriate QA QC is done, and that the numbers that you get from those labs are good numbers. And I think that's part of it, is sort of lack of regulatory methods, and then just a little bit of a lack of sort of a lack of knowledge base in what this can provide, which is what we're trying to do through these types of webinars to get that information out.
Great, thank you. You briefly mentioned isotope analyses, a lot of the work being done at the universities. Are there any labs that perform the analysis commercially and offer it commercially?
There are. So for organic compounds, for CVOCs, Microbial Insights and Pace Analytical both offer commercial analysis of both carbon and chlorine isotopes. Pace also offers analysis of deuterium and carbon in 1,4-dioxane. The University of Delaware, Neil Sturchio's lab, has a small private laboratory that will do isotopic analysis of perchlorate. And then within USGS, the Reston Isotope Lab analyzes a variety of different compounds commercially. You can send samples to them commercially. And, there are more things like nitrate isotopes. They don't do chlorinated volatiles, but they do things like nitrate isotopes. They'll do water isotopes, which can be helpful for various people. But yeah, not everything is commercially available. But a number of these, and certainly for chlorinated solvents, they're out there, and the costs, I showed the costs, they're not, they're really not extreme these days to get this done.
Great. Can you, there's a question from the New Jersey Department of Environmental Protection that relates to the cost. Can you sort of give us a range in cost, specifically for different isotopes that you may be tracking? Can you reiterate this information?
Sure. So for chlorinated organics, you say your typical site where you have PCE, TCE, cis, and vinyl chloride. Typically for carbon isotope analysis, the first compound, so let's say you want to run PCE, is probably going to be on the order of say $500 to $600. And then each additional compound you add on for carbon isotope analysis out of those same samples is going to be on the order of say 50 to 75, maybe 100 at the top. So the first compound is the most expensive because they've got to do all the work with the sample. But if there's other compounds in there that you want isotopes for, then those tend to be much cheaper. So if you want to look at all 4 compounds, you may be on the order of $800 or $900 at the tops for a single sample. Chlorine's a little bit more expensive, but not much more. And it's the same sort of scenario where chlorine for the first compound is on the order of $600 per sample, and then for each compound thereafter, it's a bit less. I don't know the cost for 1,4-dioxane. You'd have to contact PACE. I don't know if other people are doing that as well, but I know PACE is. Nitrate is fairly inexpensive through USGS. I think it's under $100 a sample. Perchlorate is fairly expensive, but that's mostly due to the amount of work it takes to purify the perchlorate from the field samples. It's collected on ion exchange resin. There's a large purification that happens. That's probably over $1,000 a sample for perchlorate.
Okay, great. This is really useful information. One last question before we let you go. As you know, CERDUP and ESCCP have made a significant investment in developing PFAS treatment technologies and site investigation tools and other relevant information, over $70 million to date. Do you believe that we can use carbon or fluorine or fluoride isotope analyses for evaluating PFAS sources?
Yeah, good question. Well, I know at this point, to my knowledge, there are no techniques worked out yet to do that. The one caveat with fluorine is that it's monoisotopic. So you can't do anything with fluorine because it only has one isotope. So you can't see enrichment. So that's kind of out the window. Now, in terms of carbon isotope analysis, I presume that's possible. These are relatively large molecules, but the larger a molecule gets, the more diluted these isotopic effects tend to be. But these are not that large, so you could see some carbon isotope fractionation. And then I guess it becomes, what is the question? So if we start to get to the point where we're really trying to understand whether these things are degrading in the environment, and we've seen one paper out of Princeton, showing degradation of at least one of these different compounds, perhaps that it might be worth going down the path to start developing those techniques. The other thing that I could see that could be important is if you're concerned about contamination. We always hear, well, if you sample in with any certain type of glove or a certain type of protective wear, you may cross-contaminate the sample. Maybe the fluorinated compounds that would be coming from that material would be different than what you would find in the environment. So maybe there's a forensic application. But at this point, I think it's a long road probably to developing techniques. And then the question is, what is the purpose of the techniques? Those are just a couple that I could think of off the top of my head. But that's it.
Great. Thank you so much for a very informative webinar that certainly highlights the really good work that CERDUP and ESCCP have done over the last couple of decades in addition to this tech transfer opportunity. So thank you again, Paul. I'd like to remind all of you that our next webinar is on Thursday, March 26th in the Resource Conservation and Resiliency The topic will be ecosystem restoration efforts to maintain DoD installation lands for future mission-related activities. We will have two speakers. Dr. Natalie Griffiths of Oak Ridge National Lab will share novel research on the impact of stream restoration efforts 15 years after implementation to assess whether restoration techniques were effective. And Dr. John Orrock of the University of Wisconsin will discuss results of a long-term study on plants in longleaf pine ecosystems to demonstrate the effect of management activities on plant population establishment, persistence, and spread. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you for your time.